Good evening, everyone. This is the third week uh, live interaction session for our course Computational Fluid Dynamics by Professor Srinivas Jayanti of Department of Chemical Engineering, IIT Madras. Myself, Manjunathan, your TA for the session from Department of Applied Mechanics, IIT Madras. So let's start our session for today. So in first and second week, we have seen in first and second section, second week, the course content was broadly about the uh, broad overview of the CFD methodology. So, in first week, we have seen calculation of flow properties over a rectangular duct, which is simple because the rectangular duct itself uh, infinite is defined with Cartesian coordinates or rectangular coordinates. So, this is an AC implementation of the CFD methodology, which was explained in week one to get you a broad overview of our subject, computational fluid dynamics. And in second week, uh, the session was on the discussion was fully on a triangular duct. Even though the chosen triangular duct is of having a regular triangle, uh, uh, you may have seen how much difficult or how much different it is from rectangle coordinate calculations. So this first and second week uh, lectures gives you a broad understanding of the subject. So the week one and week two of our subject has given a broad understanding of the subject, whereas in first week we have seen uh, about the basic methodology of computational fluid dynamics, and in second week the flow over triangular duct have which is introduced for the learners to understand how difficult or how tedious it can become when the geometry changes. So even though there is a slight change of geometry, that rectangular duct become a triangular geometry. Even then, how different or complex the system can become. So first 2 weeks gives a broad uh, overview of CFD. Whereas from the third week onwards, we are going to look in detail what are the basic steps that is involved in the CFD methodology. So in third week, we have discussed in the videos have NPTEL videos. If you have watched, then it has discussed thoroughly about the types of fluids and the types of fluid flows. So, and also how we can use differential equations to uh, address or to model the physical behavior of a fluid flows. So, basically, third week of our course is on uh, types of fluids and fluid flow, from which you will get the understanding how and why some terms are there in our CFD equations and how we can model. Model in actually it's not when I am saying model is not always equal to geometry. In CFD, uh, model is kind of model or modeling is always used uh, in coherence with approximation. So when you hear a word model or mathematical model or modeling, it is generally what we are in CFD. Uh, what we are talking about is an approximation, how we are modeling the physics or physical phenomena in terms of mathematics. That's what is broadly this word mean in CFD. And also when we talk about geometry, then we will be use geometric model or something, or geometry itself. So mostly in layman terms, when we hear the word model, what will come to our mind is a geometric model. But uh, uh, please keep in mind that whenever you in this course and or the introduction section, when we are talking about mostly the model or modeling the world means approximation. So let's move on to our session. So I will just read out the questions and give you some time to think and answer. You can inbox your answers in the chat box, and then I will explain what's the difference or more about the question. So let's start our session. Questions. First question: which property distinguishes Newtonian fluids from non-Newtonian fluids? Fairly simple question. Options are: option A, density; option B, viscosity; option C, pressure; option D, surface tension. You can inbox your answers. Please inbox your answers. A fairly simple question. And do remember, these kind of simple questions will be there in the exam also. Yes, thank you. The You are right. The answer is option B, viscosity. So the we have remember basic fluid mechanics. Uh, Viscosity is the proportionality constant that relates between stress and strain. So from that itself, you can understand that itself is the concept of Newtonian Newton's laws of viscosity. So basically, viscosity is the property which distinguishes between Newtonian and non-Newtonian fluids. And also for non-Newtonian fluids, shear stress will be related to shear strain, rate of shear strain, uh, by some method, some constant or some factor that is called viscosity. Next question. Newtonian fluid assumption is quite accurate for which of the following? So options are: option A, air; option B, water; option C, crude oil; option D, diesel. So just think about the basic how Newtonian fluid is classified, then try to answer which among the following can be considered as uh, Newtonian fluid. Please inbox your answers. So answers A, B, and D can be considered as Newtonian. Moving on to next question. The advection term in the momentum conservation equation in x direction for a constant property in a two-dimensional Newtonian fluid flow can be written as which among the following? So the question is about the advection term, only on the advection term of the momentum conservation equation and in the x direction of a two-dimensional Newtonian fluid flow. Options are option A, u into dou u by dou x plus u into dou v by dou y. Option B, u into dou v by dou x plus v into dou u by dou y. Option C, u into dou u by dou x plus v into dou u by dou y. Option D, u into dou u by dou x. So, which among the following is the advection term in the momentum conservation equation or momentum equations and in the x direction momentum equation? A fairly simple question. You can inbox your answers. The option is option C. So in the x momentum equation, here if you see uh, this gradient terms should be of x component velocity. That x component velocity is u. So this should be both u. So if you see here it is v. So option 1 is wrong. Then again if you see it is here also it is not u. That's also wrong. Then if you see here it's both u and also x and y. So this can be true. And here if you see it is only for one direction, not for two dimension. So our answer is option C. So these kind of questions will be there only to confuse you when you are facing on difficult question, and even after if you are spending a lot of time in the difficult question, then this kind of simple questions you even try, then sometimes you can confuse between these terms. So these kind of questions you can expect. Next question. The diffusion term in the two-dimensional y momentum conservation equation is given by. So the question is on which one of the following is the diffusion term in a 2D y momentum equation. Options are mu into dou square v by dou x square plus dou square v by dou y square. Option B, mu times dou square u by dou x square plus dou square u by dou y square. Option C, mu times dou square v by dou x square plus dou square u by dou y square. Option D, mu times dou square v by dou y square. So the question is on the diffusion term in the 2D y momentum equation. You can inbox your answers. The answer is A. The similar, the same logic you can use here. It is asking for y momentum equation. So in y momentum equation, the gradients will be taken. In y momentum equation, the gradients will be taken for the y components of velocity, which is v. So you have to check which if the equation is consistently having v in the denominator. Then again, if there is some confusion, we can check the denominators for the arrangement. So if you see here, first in the first option A, mu times the v is in the denominator, dou square v by dou x square plus dou square v by dou y square. So this is the right one. Also, sometimes, not sometimes, always check the other options also. Sometimes there can be more than one same answers true. So here if you see, it is both u in the denominator wrong. Here if you see, there is a mixture of v and u, that's also wrong. And here it is one dimensional. So our only right option is option A. So next question, for a Newtonian fluid, sigma yy is given by which of the following? So the principal stress in the y um, direction, that is sigma yy, is given by which of the following? Option A, half mu times dou ui by dou xj plus dou uj by dou xi, which is in a tensor form. Option B, half mu times dou u by dou y plus dou v by dou x. Option C, mu times dou v by dou y. Option D, none of the above. So our question is for Newtonian fluid, sigma yy is given by which of the following? You can inbox your answers. Answer is option D, none of the above. So, if you if you remember the shear tensor metric sigma yy given by minus p plus 2 times dou v by dou y. That is what there is uh, uh, in the formation. So this is not at all in the form. So this, in Newton fluid, it can become 0 or p according to the conditions. So this is what therefore axial stress. What in the options what we have given for the strain components only, not the axial components is not there in the options. Next question. Next question on the type of non-Newtonian fluids. Options are which type of non-Newtonian fluid exhibits shear thickening behavior. So options are option A dilatant fluid, option B pseudoplastic fluid, option C Bingham plastic fluid, option D ideal gas. Sorry. So the question is which among the following will exhibit a shear thickening behavior? You can inbox your answers. So answer is option A dilatant fluid where viscosity will increase with shear stress. So here it's shown a graph for uh, shear stress against strain rate. So for Newtonian fluids, it will be a straight line passing through origin, whereas for a non-Newtonian fluid, the dilatant sorry the for a dilatant fluid, that is shear thickening fluid, the grass will be in a concave nature, and whereas concave nature with respect to x-axis, and a pseudoplastic fluid, it will be a convex nature. So if you see shear thickening, meaning this line what is showing is like a uh, uh, slope. So this is a slope. If you see, the slope is increasing. That is, as shear stress increases, the viscosity increases. So if you take the slope here, you can see the vertical distance will be y distance will become higher, which means each this n will be greater than 1. So such a condition is called a dilatant fluid. Moving on to next question. Question 7. Blood can be categorized as which among the following? So the question is on type of uh, fluid, fluid type of the blood. Option A, Newtonian fluid. Option B, dilatant fluid. Option C, Bingham plastic fluid. Option D, pseudoplastic fluid. So the same thing, you can think what will happen to blood uh, when shear stress, that's a tangential stress, our surface is applied. Then what will happen to blood? If you think in that way, you could understand which type of fluid is blood. So our answer is, you are right. Our answer is pseudoplastic fluid, that is shear thinning fluid. So whenever some shear stress is applied on a over the blood, you can see uh, it will be the shear stress will decreases with sorry, the viscosity will decrease uh, with the application of shear stress. So such kind of fluids are known as shear thinning fluid or pseudoplastic fluid. Moving on to next question. Which phenomena causes drag on objects moving through fluids? Simple question. Only to cover the simple basics covered in the uh, week third week. The difficult question will be, we will see difficult questions towards the end of this session. So please try to answer. So which phenomena causes drag on objects moving through fluids? Option A, buoyancy. Option B, capillarity. Option C, viscosity. Option D, surface tension. Yes, you are right. Option C, viscosity. So viscosity is the basically friction between the layers of fluid. So when an object fluids, suppose these are fluid layers, when some object moves between the fluid layers, then these fluid layers will try to slow it down, or the friction provided by these fluid layers will uh, try to reduce, I mean, slow it down. Such a slowing action develops drag force or drag. Next question. Consider a flow problem with constant density and no external forces. In this case, the momentum equations simplifies to which of the following? Option A, full Navier-Stokes equations. Option B, Euler's equations. Option D, continuity equation. Option D, pressure gradient equation. So the question is on if there is no variation in density and there is no external forces are acting on the flow problem, then which of the following equation can represent that flow physics? Try to inbox your answers. You are right. Answers are Euler's equations. When this is the momentum equation, when the density is constant and there is no external forces, that is when density is constant, this time won't be there. Then again, when external forces, that is there is no body forces acting on it, this time will also go. So then the equation will essentially reduces to convection terms is equal to pressure gradient. So these equations are called Euler's equations. So our answer is option B, Euler's equations. Next question. Consider a pipe flow problem with non-inlet velocity and pressure. Which boundary condition type is needed at the outlet? Or you can consider it as needed as most suited. So the question is, for a pipe flow problem with non-inlet velocity and pressure, which boundary condition might be most suited at the outlet? Option A, Dirichlet boundary condition. Option B, Neumann boundary condition. Option C, mixed boundary condition. Option D, none of the above. Yes, you're right. Answer is option B, because for in outflow boundaries, it is better to specify the gradient of the variable. So if the here it was said like both inlet velocity and pressure is known, but better to give this gradient of the variables at the outlet boundary so that the discretization and solving become easier. Next question, what does numerical convergence refers to? Options are: option A, solution approaching the true solution with finer mesh. Option B, solution remaining constant with varying mesh size. Option C, dependence of solution on initial conditions. Option D, ability of code to run without errors. So, what does numerical convergence is means in CFD? Options are: solution approaching a true solution with finer mesh, solution remaining constant with varying mesh size. Option C, dependence of solution on initial conditions. Option D, ability of the code to run without errors. Is option A. Numerical convergence uh, means the uh, our simulated results getting closer to the true solution when our mesh is defined. Next question. The conservation of momentum equation in fluid dynamics expresses the balance between which of the following? Option A, pressure and shear stresses. Option B, inertia and viscous forces. Option C, pressure and gravitational force. Option D, buoyancy and surface tension. So the question is on momentum conservation equations. In momentum conservation equation, which of the following forces strikes a balance? Option A, pressure and shear stresses, inertia and viscous forces, pressure and gravitational force. Option D, buoyancy and surface tension. Yes, answer is option B, balance between inertia and viscous forces. So if you see in momentum equations, uh, it will be on LHS, inertia forces is equal to pressure forces plus body forces plus viscous forces. So here in the given combination, uh, if you see first one is like pressure and shear stress. So pressure and shear stress is not a valid option. So pressure forces or shear stress as a force is not mentioned. Option B, inertia. Inertia force is on the left side and viscous force are on the right side. So that's keeps it strikes a balance between. Again, if you see pressure and gravitational force as such is not there. Body force is there, but both are on the same side, so it's wrong. And again, buoyancy and surface tension is not considered while in consideration of momentum, so that's also wrong. So our answer is option B, that is inertia and viscous forces. Next question: which term in the Navier-Stokes equations represents inertial forces acting on a fluid element? So the question is on which terms of the Navier-Stokes equation represents the inertial forces acting on a fluid element. Option A, pressure gradient. Option B, viscous stress tensor. Option C, body force term. Option D, convective acceleration term. You can inbox your answers. Okay. Yes. Option D, which is the convective acceleration term, represents the inertial force in the flowing fluid. So, if you remember, the left hand side of the equation is taking u only dou u by dou t, or simply d by dt, which is the material derivative expanding, which will become dou by dou t of that quantity plus u times dou by dou x of that quantity plus v times dou by dou y of that quantity plus w times dou by dou z of that quantity. So here, if you see, this term is the temporal acceleration, which is the change happening due to the uh, with respect to time. Change in the position with respect to time is given by this term, while this term is the change happening in space, that is in gradient. So this term is known as convection or convective acceleration. So this convective acceleration, these three times, gives the inertial force acting on a fluid. This occurs due to the uh, what change of position of that uh, fluid element within the flow field. Next question. Which of the following boundary conditions is commonly used in CFD for solid walls? So the question is on boundary condition, type of boundary condition. So which of the commonly used boundary condition for solid walls in CFD? Option A, free slip boundary condition. Option B, no slip boundary condition. Option C, periodic boundary condition. Option D, inlet outlet boundary condition. You can inbox your answers. Okay, our answer is option B, no slip boundary condition. So here the no slip boundary condition is assumes zero velocity at the wall. So that's what we are establishing. So that is the wall is rigid, the wall is not moving. Such a condition is known as uh, a no slip boundary condition. Let me explain the other boundary condition also. So here, if it is no slip boundary condition means if you assume a flow field, flow is happening in xy direction. So in no slip boundary condition, meaning v x becomes 0. This flow velocity. Suppose this is the uh, inlet flow. So and this means Vx is equal to 0 at some point. So at not at some point, sorry, at what it becomes 0. X is equal to 0. So if you see, so the velocity profile will be 0 at the wall and it will be steadily increasing until it reaches the boundary layer or maximum velocity. So such a boundary condition is called no slip boundary condition. But what is this free slip boundary condition? So free slip boundary condition is like uh, du by dy is equal to 0. That is, uh, this Vx can be written as u is equal to 0 also. That is this application of a um, vertical velocity gradient in the uh, wall is known as free slip boundary condition. So it will be then the velocity profile will be like a regular one. So that variation in velocity won't be there. So this is what it is mean by that. This, if you want to remove this gradual variation or development layer, then this kind of free slip boundary conditions are given. That is dou u by dou y is equal to 0 at wall. And what is periodic boundary condition? Periodic boundary condition, by the name itself, we can say is a function of time. So any velocity, suppose u is equal to function of time. So it is varying like a sine wave or something. If u is varying, then it is called a periodic boundary condition. So not just varying, but it is repeating at regular intervals, that is time periods. For some time period f of t, it will be repeating. Uh, so such a boundary condition is known as periodic boundary condition. And inlet outlet boundary condition is the common patch or name or common condition that is given to the inlet or outlet of the domain, geometric domain. We have to, there are different types of boundary conditions. So once you have once and when you are establishing some code or something, then you have to define which type of boundary condition. So here, suppose it's relating to the uh, geometric model. So suppose this is a geometric model, rectangular duct. So this is the inlet and this is the outlet. So these two patches, what we will be defining as inlet outlet boundary condition, whereas this portion, all the other four walls will be defined as wall boundary condition. So this is some boundary condition with respect to the geometric border, not just as the physics of the problem. This is how we will be defining in when the code is developed or when we are establishing in the solver. To is simply mapping the physics with the geometry. Okay, moving on to next question. Next question. In a two-dimensional incompressible flow, which term in the Navier-Stokes equation is responsible for viscous dissipation? So the question is on viscous dissipation for a 2D incompressible flow, which term in the Navier-Stokes equation is responsible for viscous dissipation? Options are option A, convection term, option B, pressure gradient term, option C, body force term, option D, viscous stress term. Simple question, you can directly answer. Yes, our answer is option D, viscous stress time. Okay, you have a doubt where we use free slip boundary condition. Okay, as we have explained earlier, um, here if you see, uh, there will be conditions where if you see here in free slip boundary condition, Vx, that is u is not equal to 0. Only uh, du by dy is equal to 0. That is, this is exactly actually can be taken as no penetration condition, because du by dy means the vertical change, uh, change in the vertical direction, velocity change. So by applying this, what we are saying is u is not equal to 0. That is, this gradient won't exist there. This 0 to uh, uh, maximum, u maximum or u infinity, this growing field won't be applied there. Suppose you want to you don't want to study the, suppose this is a fluid domain, this is a larger part of a larger domain. So this is your fluid domain. Suppose the larger box is a your fluid domain, but you don't want to study the boundary effects or boundary layer effects. You are consider you are interested only in somewhat in the inner regions of flow. So in such conditions, actually the flow is happening outside also region, but you only want to study this. That's the control volume concept. So you are taking a control volume in somewhere inside the flow. In such conditions, this boundary condition can be applied. Or again, uh, suppose the body is moving, it's a moving wall, it's a perfectly moving wall. Suppose the flow is happening over some rotor or something, some propeller fan or something is there, and the propeller fan is moving the fluid, and in the layer there is perfect coupling, that is a perfect momentum transfer between solid and fluid wall. Then this again this free slip condition can be applied. So in such scenarios, these free slip boundary conditions can be applied. Or also, if you go a little deeper, you can see there will be some scenarios where we can't apply this wall condition in some regions when you are doing some porous media calculation or some other calculation. These because when we are coupling it with some other chemical species or some other type of flows, then there will be difficulties of solving when the velocity at the wall becomes 0. So in such scenarios also, we can go for this free slip boundary condition. I hope that answers the question. Moving on to next question. This is a problem, small problem, numerical problem. Uh, uh, Question is, consider a steady laminar flow of water with the density rho as 1000 kilogram per meter cube and viscosity as 10 raised to minus 3 Pascal seconds through a pipe with diameter 0.1 meters and average velocity 1 meter per second. Calculate the viscous dissipation per unit volume. So try to compute the answer. It's a simple direct substitution answer question. Question is on how to calculate viscous dissipation per unit volume. The properties given are density, viscosity, diameter, and average velocity, U average. And also for your previous question, where free-slip boundary condition can be used, for inviscid flows and high Reynolds number external flows can also use these kind of boundary condition. Free-slip boundary condition can be used for high Reynolds number flows. These two are practical application. I'll just explain. These are the use cases for free-slip boundary condition. So when Reynolds number is very much higher, then we may not be considered with the shear stress, or also the application where shear stresses are not uh, required. In such applications also, free slip boundary conditions are used. In the previous question itself, viscous stress time is given. So from that, try to calculate viscous dissipation. Okay, simply giving this, we know our viscous times are mu times del square u square del square u. So here that differential terms are not there, so we can directly what approximate u as the average u, and diameter as the diameter direct diameter. So by substituting, we can get here u is zero point 0.1 meter per second. Multiply with velocity, we will get 10 watts per meter cube. That is a viscous dissipation. Moving on to next question. What term in the Navier-Stokes equation is responsible for buoyancy forces in a stratified fluid? Question is on buoyancy forces. So options are option A, convection term, option B, pressure gradient term, option C, body forces term, option D, viscous stress term. Question is, what term in the Navier-Stokes equation is responsible for buoyancy forces in a stratified fluid? So we are not assigning any such forces as buoyancy forces in our Navier-Stokes equation. So which among the following terms will give the buoyancy effect in the Navier-Stokes equation? Options are option A, convection term, option B, pressure gradient term, option C, body force term, option D, viscous stress term. Clear and box your answers. Yes, option C, body force term. So the buoyancy forces are uh, in the buoyancy force effects are included in the body force term. So body force term is given by rho g. And what is stratified fluids? The question is was on force in a stratified fluid. So what is a stratified fluid? Stratified fluid is like uh, uh, the fluid having different layers where density variation is there. So if we consider an air column or ocean, ocean or some large reservoir of water, in such cases, this density, there will be density variations. So the towards the bottom layer, the fluid will be more denser than the layers above it. So such kind of fluids are called stratified fluids or stratified flow field. So in such cases, the force of body force of the uh, layer above one layer is added to it. That's why the uh, body forces represent the buoyancy effects in stratified fluids. Next question. Consider water flow through a pipe with constant velocity 2 meter per second. The density of water is 1000, can be taken as 100 kilogram per meter cube. Compute the inertial time in this case. Yes. uh, Taking inertial time is raw times dou u by dou t, that's material derivative. Even though that it is uh, I mean there is no acceleration with respect to time. The inertial, that's a conventional velocity is there, which is given by the inertial time, and it is simply a product of uh, density into our velocity, that is 2000. Next question. You wish to calculate the velocity and pressure field of laminar flow of water through the domain shown in the figure 1, which is this one. How many partial differential equation do we need to solve? So the question is on number of partial equations needed to solve a laminar flow of water through the domain shown in this figure. The domain shows a rectangular uh, duct of constant area. So how many partial differential equations are needed to solve this problem? You can inbox your answers. Actually, answer is option D, 4. Because it's a three-dimensional domain, so there will be three momentum equations and one continuity equation. So 3 plus 1, 4. Yes, while simplifying, it will reduce, but the question is how many equations we have to consider. So the answer is option D, 4. Next question. The momentum balance equation in x direction can be written as which of the following? Option A, u times dou u by dou x plus v times dou v by dou y plus w times dou u by dou z is equal to minus 1 by rho times dou p by dou x plus mu by rho times dou square u by dou x square plus dou square v by dou y square plus dou square w by dou z square. Option B, u times dou u by dou x, v times dou u by dou y plus w times dou u by dou z is equal to minus 1 by rho times dou p by dou x plus mu by rho times dou square u by dou x square, dou square u by dou y square plus dou square w by dou z square. Option C, u times dou u by dou x plus v times dou u by dou y plus w times dou u by dou z is equal to minus 1 by rho dou p by dou x plus mu by rho dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square. Option D, none of the above. The question is on x direction momentum equation. Which among the following represents momentum equation in x direction? Yes, the answer is option C. So again, as we have discussed in two of the questions above, the question is on here x direction momentum equation. So x direction velocity time is u. So you have to check whether uh, which of the following has uh, consistent u times on the uh, denominator of all the gradient types. So if you see here, is here u is here it's v. So it is first is not the right answer. Again, if you check the second equation, here the LHS is right, u, and if you check the right hand side, this time is true, dou p by dou x, m by rho, dou square, here u is there, here it's v, and here is w. So again, it is wrong. So for third option, it's u. So LHS is right. And checking the right side, you can see here it's x, and here you can see it's u, and u. So our right answer is option C. Moving on to next question. Which numerical method is most commonly used to solve discretized Navier-Stokes equations in CFD? Option A, finite element method. Option B, finite volume method. Option C, finite difference method. Option D, spectral method. So the question is, which of the following method is most commonly used to solve discretized Navier-Stokes equation in CFD? Yes, option B, finite volume method. So these kind of questions are just to confuse you. Here the catchword is most commonly used. If you see some solvers like COMSOL and all used finite element method, and finite difference method is what you will be learning from the basics of CFD. So here the most word is the key phrase. So our answer is finite volume method, option B. Next question. In a CFD simulation with a moving object, which machine technique is most suitable to adapt to the object motion? So the question is about uh, when we are simulating a CFD simulation with a moving object in it, which of the following machine technique is most suitable to adapt to the object's motion? Option A, static mesh with fine resolution around the object. Option B, offset mesh with separate meshes for object and background. Option C, deforming mesh that continuously adjusts to object's position. Option D, all of the above are equally applicable. So let's see what all these meshes are. So first option is static mesh with a fine resolution around the object. In this picture, you can see uh, what it is, a fine resolution around the object. Here this yellow color region is a fluid region, and this red color region is solid region. So if you can see here, there is a fine resolution in the grids uh, compared to the fluid and solid region, where in the interface region there is a fine resolution. So such type of mesh are called hybrid meshes, uh, where more than one type of meshing is there. So these figures show hybrid meshes with different types of meshing. So this is a tetrahedral element. These elements you can see, this is a tetrahedral element. Well, this is hexahedral elements, or uh, almost a rectangular kind of elements. So presence of two different types of mesh is called hybrid meshes, and this is what to give a fine resolution in the around the object. So this is mostly used to uh, study when there is we are interested in the boundary layer or the interaction of law or a solid object. This doesn't mean that uh, this is this kind of mesh establishment doesn't need that the object is moving. So when there is fluid and solid is present, and we are interested in the property changes or flow phenomena uh, in the near layers of that solid fluid uh, interaction region, then this kind of fine resolutions are given. These are called prism cells also. Mostly in CFD, you may have known this prism layers, stratified layers. This is what fine resolution with static mesh. And next one, this is the overset mesh. If you can see, here there are two type of meshes. Here is a Cartesian mesh in white color, which is grid A, and above that there is grid B, which has having another kind of mesh. So this kind of mesh is called overset mesh. Here is also here is a structured uh, background mesh and unstructured overset mesh. Here, if you see another explanation, I mean another establishment of one profile, NACA profile, or some kind of aerodynamic foil shape here. So these kind of meshes where one mesh is uh, set over the another mesh is called overset meshes. And next one is deforming mesh. So if you see this picture, this portion is a solid uh, portion and this is the fluid portion. So if you see in these two images, the elements are changing. Suppose if you are checking this element here and corresponding element here is larger in size. So it's like according to the moving object's motion, the set is the mesh is kind of changing its shape. That is, it is getting deformed. Such kind of meshes are called deforming meshes. So our question was, which is the most suitable mesh type to adapt the object's motion? So from the explanation, I think it will be clear that which type of mesh is required. So our answer is option C. Deforming mesh is most preferred to mm, what to all the capture the flow property changes occurring around a moving object. So these kind of deforming meshes are most commonly used in FSI, which is fluid structure interaction. Moving on to next question. Question is on which type of flow problem is generally more suited for FEM compared to FEM, where FVM is the finite volume method and FEM is finite element method. Option A, heat transfer with complex material properties. Option B, turbulent flow involving complex boundary layers. Option C, linear elasticity analysis of a solid structure. Option D, both A and C. Write in box the answer. Our answer is the question was on which type of problem is most suited for finite volume method. So finite volume method is most suited for uh, problems involving fluid flow, which is having generally a dominant fluid flow is there. So among the following, uh, here the type of it first option, it is not exactly mentioning which type of uh, simulation is there. Mm, uh, Flow problem exactly it is not explicitly mentioning. So heat transfer with complex material property will be difficult to solve with FEM. Whereas option B, turbulent flow involving complex boundary layers. This will be more suited to solve with finite volume method. And in option C, it is saying that solid structure. So linear elasticity with solid structure, even if it is FSI problem, like a fluid structure interaction, there, like the example I have shown before. In such condition also, we can't solve with equation with linear elasticity using uh, finite volume method. So option C is wrong. So when option C is wrong, option D automatically gets wrong. So answer is option B. Whereas our finite element method can do better in heat transfer and solid mechanics problems. Heat transfer, like if you have a composite material or solid heat transfer through solid, excuse me, such kind of cases, a finite element method will be most suited. Uh, Next question. Moving on to next question. Which statement is true about computational cost of different methods? So the options here compares the computational cost of different computational methods. Option A, FDM is always most efficient method. Option B, finite element method is generally more expensive than FDM due to element integration. Option C, the cost depends on specific problem, mesh complexity, and desired accuracy. Option D, both finite volume method and finite element method are guaranteed to be cheaper than FDM. So, which among the following statements are true with respect to the computational cost? Our answer is option C, where this computational cost is always depending on uh, the specific problem actually. The, how that specific problem is and how complex the mesh is and what is the accuracy desired. So uh, there are some rules, thumb rules used in industries to reduce computational cost. So, like if you are doing research or something, then you will be doing more of grid independence studies. But uh, for actual purpose, there will be having some set levels of refinement uh, for which you will be running the simulation itself directly. So there won't be some grid independent study or something. So like that, it will be uh, there is no universal rule. It will be always depend on the accuracy you need, and also on the particular flow problem and geometry involved. So for even for simple problem through a duct or something, if the duct shape is very difficult, then we will be needing a very complex mesh to capture the fine turns and bends of that duct. So which will in turn make that problem more computationally expensive. So it is always dependent on the problem. Next question. Which type of solver is commonly used for both finite volume method and finite element method discretizations in CFD? Option A, direct solvers. Option B, iterative solvers. Option C, spectral methods based on Fourier transform. Option D, all of the above are equally applicable. So the question is on which which type of solver is commonly used for both finite volume and finite element method discretizations in CFD. Is option B, iterative solvers. But the catch is where finite element method, mostly direct solvers will be preferred for finite element method, but computations using uh, CFD, computations of CFD using finite element method will mostly preferred by iterative solvers. So some similar methods in for direct solvers are kind of LU decomposition method and all. Whereas iterative solvers are kind of using some iterative method like Gauss Seidel and all. So these direct solvers are more expensive, while it is more accurate, but it will be more computationally expensive, and there will be some order of limitations and all. This can be used for small scale CFD, these direct solvers, but iterative solvers are mostly preferred for CFD uh, with uh, using finite volume or finite element method. So the answer is option B, iterative solvers. Next question. What is the main purpose of mesh refinement in specific regions of CFD domain? The question is on mesh refinement in specific region of CFD domain. Option A, reduce computational cost. Option B, capture complex geometry details. Option C, resolve high gradients and boundary layer physics. Option D, ensure mesh conformity. Answer is option C. If you remember, we have discussed in types of mesh in one of the previous problems, like uh, when there is a solid geometry is there, fluid region is also there. So mesh refinement is mostly given in the regions where boundary layers or some uh, region where high gradients of velocities or fluid properties exist. So this fine meshing, these refinements are needed mostly to capture this uh, but high gradients, because if you see this viscous terms, where is dou square u by dou x square, all those terms, these kind of higher order terms uh, should be uh, these viscous terms, and these can only be calculated where this dx, that is delta x square, that geometry uh, value becomes so small. So there we need fine meshing or fine distance, I mean very small delta axis. So in such cases, such places, mesh refinement is mostly needed. Yes, all other thing apart from option A, that is reduced computational cost, is not there, because when the mesh is getting refined, the computation cost will go up. So option A is not wrong, but option B and option D uh, will also feel like the right answers. But the actual intention behind mesh refinement is to uh, give a fine refinement so as the flow gradients can be resolved and uh, calculated to the extent of accuracy that we need. So answer is option C. Next question. What is the key concept behind mesh independent studies in CFD? Option A, analyzing the mesh quality based on element shape. Option B, verifying the simulation results remain unchanged with increasing mesh density. Option C, validating the CFD model against experimental data. Option D, reducing the overall memory consumption of the mesh. So, which of the following idea is the key concept behind mesh independent studies or grid independent studies in CFD? Yes, option B, that the verifying that the simulation results are simulation results remain unchanged with the increasing mesh density. So from the name itself, it is mesh independence or grid independent studies. So when the study is becoming independent of the grid size or mesh size, that is what is meant by mesh independent studies. So simply to put it, so we have like a lot of gradient times dou u by dou x times in our equation. So this is kind of approximation is to the delta x distance in our grid. So element sizes. So not exactly, but somewhat proportional to this thing. So when this delta x becomes smaller and smaller uh, than some particular uh, threshold value, then we can see how this time changes. Dou u by the variation of u with respect to x can will vary until some delta x. After that, it won't be affected because suppose u is varying like this. So to capture the gradient, how much finer this delta x should be there. So we have reached some particular delta x. After that, uh, what? Uh, Reducing this delta x further won't change that uh, gradient or that slope. So suppose w- the slope is kind of, we are assuming this curve portion as a straight line for some small infinitesimal delta x. So you, the next study we are refining means we are reducing this delta x, but still it is only covering a small portion of the original straight line which was fitted by the previous delta x. So such a condition is called grid independence. So the such kind of studies are done only to find uh, that our grid size does not affect our property calculation. So such kind of studies are called grid independent studies. So that's all for today. Thank you for joining. Thank you.